alarm system has 3 different control panels in 3 different locations. To enable the system, switches in the at least 2 of the panels must be in the on position. If fewer than 2 are in the on position, the system is disabled. Design a circuit to control the switches. So we have 3 switches. I'll call them P, Q, and R. So we have 3 inputs, P, Q, and R. We're going to start by building an input-output table for this circuit. So I list off all 8 possibilities for my inputs P, Q, and R. According to this situation, to enable the system, or in other words, for S to be 1, switches in at least 2 of the panels must be in the on position, meaning that if at least 2 of these inputs are a 1, then the output is a 1. So row 1 is a 1, row 2 is a 1, row 3 is a 1, but row 4 is a 0 because only one switch is on. And then we can finish this input-output table, and now we can see what makes our output true. Either P, Q, and R have to all be true, or P and Q have to be true, or P and R have to be true, and Q has to be false. So either P, Q, and R have to all have an input signal of 1, or P has a signal of 1, Q has a signal of 1, and R has a signal of 0, or P is 1, Q is 0, and R is 1, or P is 0, Q is 1, and R is 1. Now let's consider this first 2 rows at the same time for a second. If you notice that if P and Q are both 1, then it doesn't matter what R is, the output of S will be 1. So we can say that S is 1 precisely when P and Q is true, regardless of what R is. So under these assumptions, where P is true and Q is true, then S is also going to be true, or have an output signal of 1. For the third row, we would need P to be true, Q would need to be turned off, and R needs to be on. So these assumptions would lead to an output of 1 for S. And lastly, if P is false, and Q is true, and R is true, then I have an output of 1. So if either of these 3 specific assumptions are made, then my output is true. So that means the Boolean expression for this circuit is P and Q, or P and not Q and R, or not P and Q and R. So now that we have the Boolean expression that represents our circuit, now we can build the circuit. So we're going to have P, Q, and R. Now at some point we're going to need not Q and we're going to need not P. So let's negate P and Q first. Okay, so we're going to have 3 AND gates for each of these very specific situations. And then after we build these AND gates, we're going to need an OR gate to combine all 3 of these expressions that we build. Okay, so now that we have the latter half of the circuit, now we need to figure out what goes in each AND gate. The first AND gate is going to represent P and Q. So we need the input for P and the input for Q. Now we have to be careful because these outputs right here from P and Q are the outputs of NOT gates, which is not P and not Q. So we want to make a split at P and at Q before the NOT gates. And that's our P and Q, and we need to bring those to the inputs of this AND gate. Okay, so that's our first AND gate. The next AND gate, we need P and not Q and R. So I'm going to create another split right here from P and bring that input into this AND gate. So that's P. Next, I need not Q, which I have right here already built. And then I need the input from R. So that's the 3 inputs to my second AND gate. And to build this last AND gate, I need not P and Q and R. So I already have not P built. I'm going to bring that down. Next, I need Q. I'm going to make another split from Q before the NOT gate, so I get a clean signal from Q. And then next, I need R, which means I need to create a split from my R input signal here and connect that with my AND gate. And that completes this circuit. My output here would be S. Thanks everyone, and I'll see you in the next video.